Okay, let's get rolling. Uh, First of all, I know I talked about it last class, but in case you haven't already signed up, make sure you're all getting onto our Slack channel. So that's cuwcs.slack.com. And then you create your account up here. Make sure you go and do it with your cuw.edu email address. And that will get you into our Slack channel. And then once you're in there, make sure you join the CSC200 group. So that'll you'll automatically join the general channel, go into the CSC200 group. If you don't see it there, if you go under channels or something like that, under channels and hit the little plus sign, you can browse channels and it'll find it in there. So get into at least those two groups. There are some other groups in there, like the CS club group that was just announced in the general channel by Emily the other day. Let's see, right up here, she invited people to join the CS club channel. Encourage you to do that as well, so you can come to the computer science club events and get updates about them and stuff like that. They're actually already starting a thing. We're going to do like study groups and stuff like that with food and that kind of stuff. I think either weekly or bi-weekly, but in any case, go and find out about that stuff. So highly encourage you to get involved there. There's also a job posting thing up for a couple of jobs in the computer science department dealing with our makerspace down in the Plaster building. So you can check out that PDF and see if any of those jobs seem to fit your interest or whatever. All right, questions about any of that? Okie dokie. So let's keep going, and we were just getting ready to talk about the CPU, but we're going to start by looking at some C++ code just to get the ball rolling today. Actually, I'll do it in C initially. You know, we talked, what's the job of a computer programming language near the end of class last time, and ultimately it's to tell this guy what to do, right? Cut through all the crap, don't have to talk about it in technical jargon. We're telling computers what to do. All right, and that's why we need to learn this programming language. Well, we need to learn programming as a skill set because we're already used to talking to human beings, telling human beings what to do, or at least conveying information to a human being. Where now we need to train ourselves to talk to this guy right here. And hopefully today we're going to put some of those pieces together so we understand why it's so different. All right, so for the class, we're going to be using an online C and C++ compiler. If you want to use something else on your own computer, you can. So we're going to be using this thing called onlinegdb.com. It's not necessarily because I think it's the greatest thing since sliced bread. It's that it doesn't matter whether you have a Mac or a PC or Linux, you know, whatever. I don't have to deal with having, you know, 40 different students installing different things and saying such and such isn't working. If you were asking me what I might choose to use for C++ programming myself, I might suggest Eclipse for C++ developers. So that's at eclipse.org. And then go to downloads. And you could actually just get their full ID and then choose the C++ thing, or I think you can actually choose a specific package. Eclipse IDE for C and C++ developers. Eclipse.org, this website. But officially, I am not supporting that. So don't email me saying that, oh, I couldn't get Eclipse installed on my computer. That's the reason why we're not using that. Okay. So we're going to use something that's running out of a website so you can focus on the programming, not getting some piece of software installed. All right. So you can choose your poison. If you want to start with the online thing and dabble with this, you can. But that's the current scoop. Similarly, Visual Studio is another C++ development environment that will be more professional than what we're going to be using in here, not necessarily easier to use. So certainly for a little bit, our website thing that we're going to be doing in here is probably going to be your path of least resistance, because you're going to have enough headaches just trying to get C++ syntax and things like that working. All right. So officially, my recommendation is to use online GDB.com. This guy, onlinegdb.com, and it's in the slides. I have a link to it here in the slides. And I think I also have a link to it on Blackboard. All right, so that's what we're officially going to use, because if you go to this website, poof, you have it installed. Done. Okay, so if you can't go to this website, I guess I will support that. You'll send me an email saying I can't go to this website, and I'll say type in this website. And it should all work. Okay, so we're going to look at a hello world in C++, or in C example today. I'll actually show you C and C++ in this example, just to see what a simple program looks like. And actually, when you first go to this website, it already has a hello world program working in here. We're just going to kind of deconstruct this and talk about the different parts and that kind of stuff. So when you first come to the page, you should see something that looks like this. Select your language up here in the upper right. For us, you can choose C or C++. I'm going to choose C initially. But we're ultimately going to be using C++ in here, because towards right after midterms is when we start doing object-oriented stuff, and C doesn't support that. So, but they're identical up until that point. Okay. So now if you hit run, you should see hello world spit out to the screen. In fact, you can even just choose C++ as your language initially, because that's where we're going to end up in this class. There won't be any difference leading up to this. All right, so now let's kind of break this down and see what's going on here. So I'm going to make a couple of statements here, and these are truths among all programming languages. So again, we're trying to focus on computer programming as a skill set, as opposed to a specific language. We just happen to be using C and C++ in here. All right, so one truth, and I might have it on another slide in here, but I'll recreate it here. All programs begin and end with main. Okay, whatever computer programming language you're using, somewhere, even if it's not obviously visible, somewhere there will be a main method or a main function that exists. And when you run that program, it will start at line 1 of main and start cooking from there. So this program I have right here, we have this thing called main. And line 1 says, print something to the screen. Hello world, printf. All right. And then the very last thing, we have a return 0 in this particular case. And this is something that's kind of left over from the history. This kind of is our first rationale on why I'm using C and C++ in here rather than a more modern language. Not to say that, I mean, if you go and look at most popular languages today, C and C++ are probably still in the top 3. And in fact, in many times, they're probably the most popular language. So it's not like I'm teaching you this tool that's not useful. It's actually a quite popular language still, especially for embedded systems, like writing software for like dishwashers and things like that, as well as the video game industry. But it's also it has the added benefit for us of giving us a strong technical foundation to build our computer programming skill set on top of. All right. So notice here that main returns a value. Okay, so this guy is something that's called a function, and we're going to write functions here, so don't worry too much about the exact details of this. But this thing right here, this main that I said all programs begin and end with main, it spits out an integer when it's done. And this is something that is not common in modern programming languages for a very specific reason. So I might say, why does main return an int in C? In C++, it actually doesn't have to return an int. And in fact, I bet this is using a new enough version of the C compiler that it doesn't have to either. I just want to be able to give you the right background for what you're going to be using here. All right, so C++ still requires the int. Yeah. Yeah, their C++ compiler still requires you to put an int in front here. I'm actually going to leave this like this because it's part of my explanation I'm about to give. But doesn't really matter for us. This is more of the history lesson of where this comes from. So we're going to say in an older language like C and C++, it's common for the main method to return an integer. And the question is why? C has been around since the late 1960s. Couple of minutes. Now, when you look at operating systems from back then, which were few and far between, most of these operating systems were Unix-based operating systems, which were completely command prompt. Your entire screen looked like this. You didn't have a mouse to click on or icons to double click on and stuff like that. So you would run programs from the command line like this. Right. Yeah. I mean, you didn't have any sort of graphics, which meant when you ran a program, in order to determine if that program worked, it might spit out an error code. Like right now, you run Microsoft Word or something like that, it crashes on you and it gives you the pop-up, you know, something died, yada, 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 click OK to continue, right? It gave you an error code. It gave you something that, you know, it always says, you know, do you want to send this information to Microsoft or whatever? You know, that's just going into a black hole somewhere probably. But, you know, you've seen that before where software screams at you and then you have to, you know, gives you the option to send an error report to someplace else. Well, that's a very modern thing where not only is it showing you visually all the random crap that you don't know what it's talking about, it's also saying I've generated a report in the background that I will send to Microsoft on your behalf or whatever to help them improve their software. So that's a modern approach to having software that has some kind of error code. Historically, when you ran a computer program, it would result in a 0 if everything went fine, or it would have one of possibly many, many, many error codes that you could utilize to decide what went wrong. And you've seen these actually in like web pages. You might get a error 500 or something like that on a web page, or an internal error 404, page not found. So, you know, presumably since they got all the way up to 404, there must be a zillion HTML or HTTP. It's the protocol for websites. There must be a zillion HTTP error codes that each one means something different, right? And depending on what that error code is, you're a, you know, server manager person, you might decide, oh, well, because of this error code, I need to go and fix this problem, or this other error code, I need to go fix this other problem, that kind of stuff. That is based on this history of programs used to just run from the command line here, and there needed to be some way of saying something went wrong, or possibly something went right. Because, you know, when you wrote programs historically, a lot of times you were using other programs in conjunction with another program. So you might say, I'm only going to do this if the program I ran right before this successfully completed. Something like that. All right. So that's why at the end of this code here, well, initially main says, I'm going to spit out an integer. All programs begin and end with main. So when I run this program, it's going to, and I'll actually steal this here to show you the how this might run on your computer directly. But when I run this program, it's going to spit out an integer when it's done. And if I care, I can look at that integer and see, did everything go successfully or did something else happen? A modern programmer is very rarely going to use that kind of thing. Okay. But that's why this stuff still exists, because this is a language from the late 60s. When you're writing code in Java, and I'll show you a couple of different examples here. So we'll kind of look at examples of the Hello World program through some different vintages. All right, but I'm also I'm gonna leave this online debugger thing here for a few minutes and do this just directly on my computer, just to kind of show you what's actually happening under the hood when you click this little play button that says run. Okay, because that's doing some magic for you. You can kind of think about this. I was talking to a student after class on Tuesday. If you learn to drive with a stick shift, and then somebody introduces you to an automatic transmission, you kind of appreciate, oh, this is what it's doing for me. Now, when you're young, stick shifts are kind of fun, right? But then it's like, okay, I can't hold my coffee and things like that at the same time because you got extra crap that's going on. Okay, so when you're young, it's fun to really feel like you're driving your vehicle. But later on, when you're just kind of chilling, there's something to be said for automatic transmissions. Now, if you want to go farther back than that for something you will appreciate, even though none of you had to deal with this, but years and years and years and years ago, early days of cars, to turn your car on, you used to have to get out and crank the front of it, kind of like pulling the ripcord on a lawnmower. You had to do that with your car a long time ago, way before me. Okay. Now, wouldn't that suck, period, but especially in the winter? So you kind of appreciate that you could just get in the car and you turn the key and it just starts. Okay. Now we kind of have a couple of steps in between. Now we have fuel injected engines where you turn it and just something is happening under the hood where it gets enough fuel going into the motor so it ignites right away, so your car just starts right up. As opposed to if you've ever been on a boat, especially a little bit older boat, you got that little squeeze ball thing where you're squeezing some fuel into the motor before you try to turn it on, so stuff starts exploding in there, combustion engines. So we can certainly see that there are some conveniences that we can appreciate, even if we still think it's fun to drive a stick shift, right? We don't want to crank the engine on the outside of the car when it's -5. All right, so the same thing kind of goes here. This run button up here is kind of like fuel injection or turning the key or an automatic transmission, whatever. It's a convenience that's doing some stuff for you that's still happening under the hood. All right, so we're going to reveal a little bit of that today, and I'll explain this stuff kind of as we're doing it. So I'm going to kind of roll back the clock here, and we'll pretend like we're on an old style computer that doesn't have a graphical user interface. And we're going to go ahead and use a command line text editor to write our Hello World program in C. All right. So the text editor I'm going to use is one called VI. Probably the oldest of the oldest text editors that existed. So we'll call this guy hello 200.c. All right, so I'm in an empty, you could think of this like a notepad or something like that, but this is completely for the command line. I don't have access to a mouse in here or anything like that. So I'm going to start typing my C program. So I have to first include a library. I'm bringing a library into this code, and this allows me to do standard input and output. Write stuff out to the screen, read stuff in from the user. Kind of your basic stuff that you might want to do in your program. Okay. Even today, our modern programs, we don't necessarily do this that much. We're not writing directly to our screen or reading in directly from the user. We typically are writing to like a label that's showing up on a user interface thing, or reading in from a text box, or something like that you typed in some information, then hit a submit button. So the nature of our programs today are more event driven. Click buttons, things happen. Where historically, when we had, let's say, less complicated programs, and very much like the programs that we're initially going to write when we're learning program, we're learning old style programming because that's where the fundamentals exist. Then we'll start layering on top of it pretty interfaces and event-driven stuff and things like that. But we got to get the fundamentals first. All right. So if I want to write stuff out to the user and read stuff in from the user, I'm going to need the standard input output library. So that's what that first line does. Then I'm going to create my main method. And I'm going to go ahead and put those, the thing you saw me type in here. We'll talk about that in a second. So I'm going to say int argc, char pointer pointer, v. I'm not going to use those for the moment. And then I'm going to say printf hello world. And I'll go ahead just to match it. I'm going to say return 0 here, but I don't actually have to do that. And I usually wouldn't do that for a program like this because I don't actually care whether it worked or not from another computer program's perspective. I'm going to run this, and if I get the output I expected on the screen, I kind of know it worked. And if I don't get the output I expected on the screen, I'm going to jump back in here and start making some changes. That return 0 thing is made more for posterity, where I'm not actually going to look at this value that gets returned. But that's where it came from. If some other program was interested in the value that just came out of there, that would be helpful. All right, so I've written my program. All I've done at this point is I have written some text inside of a file that I've named something.c. All right, so my MIME type for this file, the .c, the extension, says this is a C program. Now I'm going to go ahead and save this. Now again, I don't have a mouse in a command line text editor. So VI, you actually issue commands to VI. So I have to go to insert mode by pressing escape, which also brings up my thing from Zoom apparently. Okay, insert mode, and then I'm going to put a colon WQ that says write this, so kind of save the file and then quit the text editor. So I just wrote something in a text editor. That's no different than using Notepad on your Windows machine and then hitting save. All right, but this is just the old school way of using a Unix-based computer or something like that. I'm on a Mac here with Macs based on top of Unix, so this is what's called a Unix terminal that I'm looking at here. All right, so right now I have just a plain Jane text file called hello200.c. All right. Now, if I want to run this program, I need to first compile it. So we have a tool. Let me just put this in the slides real quick. Or error messages. I'm sure this is already on a slide as well, but we'll just be on there more than once. So we have this thing called a compiler. So a compiler converts high-level code, so code like a C program, into low-level code. Ultimately, zeros and ones that the CPU understands. And we're going to talk about the nature of the CPU today as well. That's kind of what today's lecture is all about, is how do we go from a C program to something that actually runs on our computer and understanding what's actually occurring under the hood. Okay. With the expectation that this is that theoretical foundation that we're building our knowledge on top of. It's important, but as you've already seen, you can just hit the pretty run button and your program goes. And that's true in Eclipse as well. If you use one of those other tools I gave, they give you the play button to just run your program as well. You won't have to do these steps that I'm doing behind the scenes here, but I want you to appreciate that those things exist. Those are things you actually have to do. All right, make some sense? So we're going to use the C compiler to convert that text, that high-level C code that we just wrote, into something that the computer program, the computer understands. All right, so I'm going to go ahead and just show you our code here real quick. You've already seen it, but there's a program on Unix called cat that just spits stuff out to the screen. So there's the contents of that file. The contents of hello200.c looks like that. Now the C compiler we're going to use, well, that I'm going to use here, that is also used by that online one, but you won't have to directly use it. The C compiler is, the program's called GCC. All right, so this is the GNU C compiler, GCC. And when you run this program, you have to give it the name of the file you want it to compile. So you're giving it a command line argument. So I'm going to say, I want you to compile hello200.c. What does the compiler do? It converts that high-level C code, in this case, into something that the CPU will understand. So I'll go ahead and press enter on there. It'll think for a second, and then poof, nothing happened, seemingly. But it did just create a new file called a.out, which is my executable. All right, so if I do there's my a.out file I just created. Now, if I use that exact same command I used before to spit out the contents of a file, remember I used cat here to look at the contents of my C file. If I use that on that a.out file, I get weird stuff. Okay, and this is just its interpretation of that executable. A.out is an executable program that's understood by this computer. I promise that before I got to this step, some other things that look even more cryptic than this happened behind the scenes. So we're just going to throw this into the category of this isn't really human readable. All right, this is something that the computer operating system must use to accomplish its task. But now if I want to go ahead and run my program, I'll run a.out, and there's my hello world. So I went from the C program in a text file, ran it through the compiler, which prepared it into an executable that could be run by the computer, and then I actually executed it. So those steps are the same steps that happen when I hit that run button. Make sense? That's what's happening behind the scenes. Okay, questions about that? Okie dokie. Now, we want to talk a little bit more about what's actually happening when I do this GCC hello200.c. That compiler, when it converts your high-level code into low-level code. I probably have this on a slide somewhere, but I'll just skip it when I get to it later on. I'll just write it again right now. There are three kinds of programming languages. We have machine code, which is zeros and ones. We have low-level code, which has a one-to-one relationship with the CPU. And we have high-level code, which has a one-to-many relationship with the CPU. Now, what does that ultimately mean? Well, we talked a little bit last time that the language that the computer ultimately speaks is zeros and ones, not for human consumption. We don't want to have that 2-button keyboard where we're just tapping out zeros and ones. Well, BIOS is the thing that hands off between the software that runs on your computer's motherboard to the actual operating system. So it's kind of like a small operating system, so kind of unrelated to this. All right, so now when I say this one-to-one relationship with the CPU versus this one-to-many relationship with the CPU, that requires us to kind of understand the nature of the CPU. All right, so the CPU, I think I mentioned it probably right at the end of class last time. I like to think of it as a collection of magic tricks. All right, I probably have my hand up like this, doing something silly. Okay, so I'll do something like, everybody raise their hand, wiggle your thumb like that. It's like, many of you can do this. Is you're not impressed by this? You're not impressed by this? A human being, if we pretend like we're a CPU, there's all these little tiny unimpressive things that we know how to do, right? And if we put those things together in a specific sequence, we can actually accomplish some pretty cool tasks. Make sense? but we still need to put those together in that interesting sequence to actually accomplish some sort of task. Now, that comes naturally for some of us. We talked about walking and things, stuff like that last class, where, you know, it's such a complex thing, but we don't even think about it. Okay. But through practice, we've realized how to do some different things, and it comes very naturally to us. But now, as a human being, we're having to tell this computer what to do. I want you to think about that CPU as kind of being like a very limited human being, where it knows how to do it's a pretty big set of things, but each one of those things is a little tiny move. You know, like the CPU might know how to do that. It might know how to do that. And, you know, probably 1,000 other little tiny things that aren't all that interesting in and of themselves. But when you have the CPU perform one magic trick followed by another magic trick followed by another magic trick in a row, something interesting might actually occur. Okay. That is a one-to-one relationship with the CPU. If I tell the CPU to perform magic trick 32, followed by magic trick 121, followed by magic trick 3, do those 3 things, and most programs are going to be more like do those 30 things or 50 things or 600 things in a row to accomplish anything interesting. But at that point, the CPU will do its task. While a human being can operate at that level, it's still not fun for us as a programmer. Every now and then, we might like to get in there and really have a lot of control over the details of what the computer is doing, all right, what the CPU is actually doing. But most of the time, human beings, we prefer power tools. We're leveraging something like that compiler that turns our high-level code, things like our Hello World program here. This is printing Hello World to the screen. We can probably imagine that there's quite a bit more to that meets the eye than that one line of code. So as a human being, we wrote one line of C code, and then we ran that through the compiler, which translated that into all of the magic tricks that are required to get Hello World spit out on the screen, which is a lot of magic tricks. Make sense? So, machine code, we're going to understand it, but we're definitely not going to use it. In the 325 class, the computer organization class, you'll use it a lot more, like actually looking at the zeros and ones. I cover binary and things like that in here. But in terms of you as a computer scientist using the zeros and ones skill as a daily part of your job, it's not going to be very common. Similarly, working with a low-level language, we typically call this an assembly language. So this is the exact language of a particular processor. So if your computer has an Intel processor in it, or an AMD processor, which is Intel compatible, you have access to a assembly language of instructions, a collection of magic tricks that processor knows, that processor can hear from a person, can hear from the computer, okay? High-level code is when a human being writes one line and it converts into many, many, many magic tricks behind the scenes. But that conversion takes place by using a power tool like a compiler, which takes our one line of a C code and explodes it out into the individual magic tricks that will accomplish what the implication of that line of C code was. Make sense? So compilers, on one hand, really, really, really complex pieces of software. So difficult to write, and we'll, you know, there's a limited number of compiled languages, but they are difficult to write, but they perform a really important task that allows our lives as a computer scientist to be a lot more convenient, because we can write stuff at the high level, even though it looks like cryptic code to somebody who's not a computer programmer. It's still way less cryptic than a low-level language or a bunch of zeros and ones. Okay? So these are languages like C, C++, Java, C#, Objective-C. Those are your kind of your popular compiled high-level languages. All right. So let's look at what that output might be. Because a few minutes ago, I showed you on here that when I showed you what this executable looked like, this is the thing that actually would run on this computer. You see it's kind of gibberish, but I'll promise you what I'm about to show you here in a minute, which is actually assembly code, does not look like this. Okay, this is not assembly code we're looking at. This is an actual linked executable that's understood by this operating system, which means the following is true. What does a compiler need to work? It needs to know the target architecture. So that would be like Intel, MIPS, PowerPC, etc. For most of you, the only one you've heard of is Intel. Most of our computers have Intel-based processors. If you are, most of your cell phones have RISC-based processors, probably built out of Qualcomm processors. Snapdragon is one of the popular RISC processors out there. So if you have an Android phone, chances are you have a Snapdragon processor. If you have an Apple phone, you're running on Apple's own processors, one of their, A chips, A13, A14, Bionic chips, whatever. So they're also a reduced instruction set thing. Another one, a common one, is called ARM. So Snapdragon actually is an ARM processor. So the actual architecture is ARM from a Snapdragon processor. Yeah, which was a reduced instruction set. It was an IBM chip, but then they switched to Intel. And now they're switching back to their own silicon, which is interesting. Okay, so two things that a compiler needs. It needs to know the target architecture. That is, what magic tricks am I targeting? When you give me C code and you say I need to tell this CPU what to do, give me the list of magic tricks that I have that I get to choose from. Because for Intel, they might have this list of magic tricks. For ARM, they might have a different list of magic tricks. Many of them might accomplish the same or very similar tasks, but they have maybe magic trick 13 over here is the same thing as magic trick 21 over here. So if you're targeting ARM versus Intel, the output of that compiler might be a little bit different. So you do need to know what your target architecture is. What kind of processor is this going to run on? On top of that, you also need to know about the target operating system. Windows, Mac, Linux, Android, iOS, etc. All right, why the operating system? This is actually another power tool that exists between the high-level code and the low-level code that is the output of the compiler. So a compiler that's written for a specific operating system running on a specific architecture is an actual easier tool to write than a compiler written specifically for just an architecture. So for example, with that Hello World program, and we'll look at actually an example of a assembly language version of Hello World here in a minute. For that Hello World program, if I was writing a compiler that had to turn my C program that just had that one line, printf Hello World in it, and I had a compiler that outputted to a wall of assembly instructions that spoke directly to the Intel processor. Every single little magic trick that was required to ultimately get hello world spit out onto the screen. That would be a lot of lines of assembly code, because you're no longer leveraging the operating system like Windows or the Mac OS or Linux or whatever. You're not able to use some of the facilities built into an operating system to do some of the heavy lifting of the displaying stuff on the computer. Instead, you're talking directly to the computer's hardware. You have to have the magic tricks that tell the video card in your computer specifically to display an H, which has this ASCII code at this location on the screen, which is governed by this thing called the frame buffer. So we're down at the hardware level of these things. And if you're writing that compiler that has to output every single little tiny magic trick to ultimately talk directly to computer hardware, it's a tough task. And writing that by hand would kind of suck. Go ahead. Would compilers always what? Yeah, as long as programming has been out, compilers have been a thing. Yep. Well, actually, let me back up. Our concept of modern programming, yes, compilers have always been a thing. If you go back, let me show you a picture here. Any of those, it gives us it'll give us the right kind of thing that we're looking at here. All right, so here's a old computer. This is after they got a little bit smaller, because before this they took up like the size of a gymnasium. But in any case, this computer has a whole bunch of little what are called vacuum tubes. You can think of them like light bulbs. Okay, and each light bulb was a single 0 or a 1. So even before we had that low-level language for talking to the CPU, we used to tell the computer directly what to do by turning on light bulbs. So we didn't have a compiler then, but we were also very, very, very limited on what we could tell the computer what to do. Like adding 3 + 5 was kind of like your 15-minute gym workout type thing. You know, you had to do some stuff to accomplish that. So we've come a long way. Even in our earlier days of automated programming, we used to have these things called punch cards. Yep. So you would go through here and you would punch out these little holes, and that described which magic trick you're going to do next. And if you made a mistake, so then you would walk your stack of cards, you know, hopefully they, you know, none of them get bent, because you know how like sometimes you put a $1 bill into a soda machine, it just won't take it. You know, it's like that kind of thing. So you walk your stack of cards up to whoever's running, you know, in charge of the computer, because now you have this one computer that probably is barely more powerful than a modern day toaster. Actually probably wasn't more powerful than a modern day toaster. They would stand there and they would feed your cards in. And then they'd give you a printout of this is the results of it. And you go back and say, yep, that didn't work. And you're going to appreciate this too, because when you start writing your first programs, you're going to see that your programs are about 95% errors when you first start doing it. And you got errors on top of errors on top of errors. It's definitely one of those things, like I mentioned last class, where you need to put the reps in, you need to practice, and you're going to suck at it for a while. All right. So imagine when you had to do physical programming like this, and you spent all this time punching out cards and stuff like that, then you walked up only to get errors from your program. And you maybe had to wait 20 minutes for that result. Now, it could be longer, yeah. Okay, but now you sit there in front of your computer and, oh, you make a mistake, backspace a little bit, hit the play button again, and, you know, try it immediately. Okay, so computing has come a long way. So somewhere in that gap is where compilers kind of put programming on steroids that allowed us to start writing larger, more complex programs without human beings losing their patience to just saying, look, this just isn't for me. All right, make some sense? All right, but the second thing here, the target operating system, is pretty important. So first of all, what's an operating system? Anybody want to take a stab of give me a generic definition of what is an operating system? I gave you some examples like Mac OS, Windows. Technically, Windows is the NT kernel, new technology kernel. Before that, it was the 9X kernel. That's the actual operating system. Windows would be called a distribution. So when you install Windows on your computer, you're getting the NT kernel with a whole bunch of other applications installed, like Notepad and a web browser, things like that, that are distributed with an operating system to make it usable day one. Go ahead. Yeah, what does that mean? We've covered that you know how to read. I did question it, I have to tell you. Okay, so what are some things when you sit down in front of a computer, whether it's Windows, Mac, Linux, whatever, when you sit down in front of a computer, what are some generic things that you expect your computer to be able to do? Certainly turn on, but that's not an operating system thing, that's a button thing. Go ahead. Okay, be able to handle input output, right? Okay, when we talk about output, so that might be like spit something out on the screen. So we expect that our operating system provides for us some sort of mechanism for getting stuff out onto the screen. So it can talk to the graphics card on our behalf. So we can tell the operating system what we want. The operating system that somebody else wrote, that somebody already did the heavy lifting for knowing how to talk to the graphics card and that frame buffer and all that stuff I described, that's already been written. So we tell the operating system, show hello world on the screen, and then the operating system goes to work and does all that complicated, extra complicated stuff behind the scenes for us. Because that's something that we commonly do, right? We commonly expect to be able to display something on the monitor on an operating system. We commonly expect to be able to have input from the keyboard, input from the mouse. These run certain applications. So there's a whole set of things that we expect at the very generic level that all operating systems should provide for us. Make sense? All right, anybody want to add something to any of that? Go ahead. Sure. Yeah, run other applications that were written for it. Yeah, now we're kind of on a loop, right? You know, you wrote an application because the operating system's an application. The operating system needs to be able to run other applications, but how is it running those applications? It's providing a set of mechanisms for talking directly to the hardware that your other applications can leverage so that the people writing those applications don't have as hard of a time to write. Okay, so let's look at the output of a hello world program when it came out of a C compiler, when it was targeting the Linux operating system for the Intel processor. So we're going to just write here. This sits between the user and the hardware and provides a default set of abilities that all users expect a computer to perform. All right. So this here is hello world in Linux Intel assembly. These are the magic tricks that we're calling. All right, so I mentioned that a processor, a CPU, is a collection of magic tricks. Specifically, when you look at this, if you've had assembly before, which I know most of you have not, if you've had assembly before and you've had Intel-based assembly, you look at this and say, oh, that looks like Intel to me. It will kind of look familiar, kind of like if you're looking at English, you can identify English compared to French or German or something like that. If you've had some background in those languages, you can identify them by the naming conventions on the magic tricks. All right, but what we're going to see here is kind of the cadence of what a compiler ultimately does. So a compiler is going to take our code that looks like this. And it's going to turn it into something that looks like this. So now what we're going to do is we're going to walk through this and understand what's actually happening. Now, again, this is actually a power tool version of assembly code, because this assembly code we're looking at here leverages an operating system. It assumes that we're using the Linux operating system, which already has some stuff built into it so that the compiler didn't have to write those things for us as well. All right, so just down here at the bottom, this data section says, look, this is the thing we're going to write out, hello world, and this is the length of hello world. We're remembering a couple of things. Remember last time I said, how do human beings solve problems? Remember things, ask questions, repetition. Okay, that's how human beings solve problems. So here's an example of, and I said all programming languages have facilities for those things. Here's an example of assembly language, Intel-based assembly language having a facility for remembering some things. Remembering two pieces of information. The string we want to write out, hello world, and how long it is. That's just what that does. But what we're focusing on here is these things right here. Because what we're seeing is how does assembly language ultimately talk to, well, what is the nature of making a CPU perform some tasks? One of the magic tricks our CPU knows how to do is this thing called move. All right. And what we're doing is we're moving values into something called a hardware register. A hardware register is like a little piece of memory that lives directly on the processor. It's really, really, really fast. Okay. It's also really expensive per byte. Relatively speaking to like your desktop computer that might have 16 gigabytes of memory in it. That's very inexpensive memory relative to memory that lives directly on the CPU. But it's also much slower memory than the memory that lives right on the CPU. So when we have our computer running some code, we're often feeding off of memory that lives right on the CPU, which is not infinite amount of memory. We maybe have, we'll just make something up and say 12 hardware registers. So that means all the logic that we're performing in real time can only use at any point in time 12 physical locations that are sitting directly on the processor. Any things we need to remember outside of that, we have to then go and leverage system memory, like your 16 gigs of RAM in your computer and stuff like that, to accomplish those things. And that's going to slow stuff down. So as much as we can get running directly on the CPU, the faster output we're going to have. But notice here that the first four things are all moves. Remember, the goal of this program is ultimately to get something written to the screen. So this is a very, very, very simple C program. So what are we doing? EDX, ECX, EBX, EAX, these are all names of hardware registers. These are 32-bit registers on the Intel architecture. First thing we're doing is we're moving the length of our string into this location. Then we're moving hello world itself into this location. Then we're moving the number 1 into this location. And we're moving the number 4 into this location. Now, these 4 lines could have happened in any order. Effectively, what are we doing here? We are taking 4 values and we're storing them in very specific places on the processor for some reason. Okay. Now, let's look at what this 1 and this 4 mean. Because if you're just looking at this code, you're like, okay, just randomly the number 1 goes here and just randomly the number 4 goes here. So we already covered this. This is the length of hello world. This is the hello world itself. Now, what does this 1 represent? Operating systems typically have these things called output streams that they support. And we have 2 output streams. Actually, we have 3 IO streams. 2 of them are output streams. 1 of them is an input stream. So for our output streams, we have standard output, and we also have standard error. Most of our modern operating systems have 2 separate output streams like that. And the reason for that is so you can have your operating system can support logging error messages. So all error messages write out to standard error, even though they both have a destination of the monitor. Whether it's an error message or a normal piece of data, it spits out on the monitor. Error messages write to standard error outputs so that some system in the background can take anything that's on standard error and put it into a log file so you can go and look at it later to look at error messages or something. All right. But what we're effectively doing here is we're moving into this specific location on the processor, which output stream we want to write hello world to. Then we're moving into this hardware register, the number 4. And what's the number 4? The number 4 corresponds to what's called a system call of the operating system. You can almost think of an operating system as kind of like a software version of a CPU. So I mentioned that CPUs are like these collections of magic tricks. So magic trick number 1 might be this, magic trick number 2 might be this, that kind of stuff, right? An operating system has a collection of these things called system calls. One of those system calls is called syswrite. This is a computer program that was written by the makers of Windows, the makers of Linux, the makers of Mac OS. It was written by a computer program, it was probably written a long time ago, that did all of that heavy lifting, that ultimately said, this is how you get stuff out onto the screen of your computer. So that syswrite program is already written, it's already installed on your computer as part of the operating system. It knows how to talk directly to the graphics card through probably a graphics driver. It knows how to talk to the frame buffer that's associated with the graphics card that links to your monitor and all this stuff. All those extra details, those extra complexities, those all live inside of this program that was written by the makers of your operating system. So this is kind of our middleman here. Our program's not writing directly to the screen. Instead, we're telling the operating system this is what we want to do, and then we're letting the operating system take over from there. All right. So what are these 4 lines? This is saying, this is what I want to do. I want to use syswrite. I want to write something out to the screen. Well, I want to write something out. Where do you want to write it? I want to write it to standard output, which is to the screen. What do you want to write? I want to write that message. How long is that message? Because that means something, and sometime during this course, that'll make sense to you. This guy actually holds what's called a pointer to the very beginning of hello world. It doesn't hold the actual full string hello world. It holds the location of the H. And then this guy says, how far do I have to hop through memory until I get to the end of hello world? So we have a base address and then we have an offset. Okay, but bottom line is, this is what I want to do. And here's the 3 pieces of information that this dude needs in order to complete its task. Make sense? These 4 things could have happened in any order because they haven't actually executed yet. At this point, all we've done is we've taken 4 pieces of information and we dropped them into some buckets. That's it. Nothing interesting has actually occurred yet. Where it occurs is right here, this line. So we are interrupting the CPU. That's what this int stands for. Call an interrupt, and we call upon what's called the kernel. This is the actual operating system. And for Linux-based operating systems, the kernel is loaded at this memory address 80. So this is a bunch of setup. I've thrown 4 things into some very specific buckets. Now I'm saying, hey, Linux, go and do your thing. What does Linux do? The first thing it does is it goes and says, okay, I'm going to look in EAX because that's where I've taught you to put the what do you want to do. So he's going to go look in EAX. He's going to say, oh, okay, you want to do a syswrite. All right, well, I'm going to need 3 things from you. So it's going to say, I'm going to look in EBX. EBX tells them, where am I going to write it? What am I going to write? How long is it? So it's going to go look in those 3 places, ultimately getting the 3 pieces of information that syswrite is going to need to actually perform the magic of writing something out to the screen. That makes some sense? This guy right here was probably hundreds and hundreds of magic tricks long. We're using a power tool there. Hello world, as complex as this might look, is much more complicated than that. All those details are hidden inside of this little guy right here, syswrite. Because we're talking to our operating system here, not directly to the processor. The operating system's talking to the processor on our behalf. All right, so that's how we did the first move. So after we hit this line, now hello world is on the screen magically from this dude. Then what do we do? Well, we're going to overwrite what used to be EAX. Remember, EAX was where we put what do we want to do. We used to want to do magic trick number 4 or system call number 4, which was syswrite. Now we want to do system call number 1, which happens to correspond to sysexit. My program's done. Then we interrupt the CPU again, tell Linux to take over. Linux goes and looks at EAX, sees that there's a 1 in there, says, you want the program to exit. Well, I'll tell you what, I don't need any extra inputs for you to accomplish that. So the Linux operating system then goes and kills off that processor, the process that's running on the computer, your hello world program. In our case, it was called a.out, right? It kills off that thing, reclaims any memory it was taking up, and we move on with life. That's the full life cycle of a hello world program running on a modern day operating system that has a whole bunch of details already written for us here inside of these couple of system calls. That makes some sense? So based on your question, if we went back in time before our modern day operating systems, before programmable computers, when we had to use the punch cards, or we had to put the little light bulbs on, the vacuum tubes, we got it pretty good today. Even though we look at this and say, you know what, if you told me day one that my job as a computer scientist was to sit around and write this stuff by hand all day long, I do it for homework assignments sometimes. Maybe if every now and then I had to do it at work, I could tolerate that. But if this is more than like some fraction of 1% of my job, I'm probably out of here. That's okay, because this is not what you do as a computer scientist anymore. Because today we have tools that have abstracted this away, and we use high-level things for and then compilers to ultimately give us this. Go ahead. Yeah, these are effectively what I just said. Yeah, these are what are called comments. Yeah, these just fill in the blanks for you. All right. So this just kind of shows what life might have been like for a programmer, maybe in the 70s, something like that. We're probably hitting about the right time period. Yeah. Well, presumably syswrite might call other system calls, right? So whoever wrote Linux in this case, Linus Torvalds or one of the developers who've been working on Linux for years and years and years, there's a program that exists out there called syswrite. And syswrite probably calls upon other system calls of the operating system. So, I mean, presumably there might be thousands and thousands of lines that look like this that become a reality of that guy. We got off pretty easy if we only had to do this. That makes sense? But what's funny is human beings, we're lazy enough that we don't even want to do this. It's like, look, for a class, it's entertaining enough. And now I kind of feel smarter seeing this, but that's not for me. I like power tools, but we're going to sit here and we're going to be complaining about C and how hard C is. But we see it could be so much worse, right? Go ahead. Yeah, so this has to do with, now it gets into, that's kind of an operating systems question, but so one of the main components of an operating system is called the processor scheduler, the CPU scheduler. So if we keep it simple, we say that you have a lot of our computers today have dual or quad core or 8-core processors, things like that, where the number of cores your processor has is technically the number of things that can happen simultaneously. But let's just keep it simple and say, let's assume we have a single core processor. We'll go back to the early 2000s, late 90s, something like that. So we have a processor that can only do one thing at a time. All right. Now I could do that thing really, really, really fast. But the CPU scheduler, that software that's built into the operating system, what its job is to fake you out as an end user, thinking that all the programs you have open are all running at the same time. When actually one program's getting some CPU time, then he's paused, and then another program jumps on there and he gets a bunch of CPU time, and then he's paused, and another program gets on. And whenever he gets paused, he packs up all of his bags. It's called a context switch. He packs up all of his bags, which is all the values that are currently stored in the registers, and he stores that in system memory so that when he gets CPU time again, he can unload it back into those registers and pick up where he left off. Yeah, so to your question was basically, well, if there's 5 programs running on the computer at once and they're all having to share this CPU memory, how? And the thing is, only one of them is getting a single core at a time. Yeah, as soon as he gets kicked off, a context switch happens, which is actually super expensive. That's where computers actually slow down. That's why adding more memory and adding more cores speeds up computational things on a processor, because you can do more things at once. But it also makes the operating system harder to write, because now instead of managing a single work unit, you're now managing 4 work units for a quad core processor. Well, some things can't happen before other things, right? So now the operating system has to figure out, well, what things can I put on this processor and on this processor that aren't reliant on each other? So it actually becomes a more complex problem. Yeah. So how do people write really complex programs? You mean today? Yeah. Well, mostly today, we just rely on the compiler to figure it out. Yeah, from a computer programmer's perspective, a modern computer programmer's perspective, you know, what he asked was, if you're writing something presumably really complex, I used like Call of Duty as an example last time, you know, some really complex video game or something that uses a lot of memory, let's say. How do they do that? Well, we don't worry about it. And also keep in mind that if most of our moves, most of the ninja moves that we're using to talk to our CPU involves things like this, where we load some pieces of information and some memory things and then tell the operating system to take over from here. Effectively, even if we have 12 registers, we probably don't need more than that. If we have 12 registers per CPU core, that means that we potentially can support, most of our modern processors actually have more than 12. I'm just using 12 as an example. So based on this, if this guy is a function call, he's a function call that requires 3 inputs. So that means with 4 registers, I can support a function that takes up to 3 parameters. With 12 registers, I support a function that can take up to 11 parameters. Now we're getting, I mean, most functions don't take 11 parameters. So you support many things, and that's not really driven by the complexity of the program. If you want to think about it kind of in real life, if somebody asks you to perform a task, usually you're working with, you know, 2, 3, 4, 5 different inputs to make it happen. Somebody says, you know, I want to drive my car to a certain address. You're putting in, you know, the street address, city, state, zip, whatever, you know, not that many inputs to make it work. So that's not really a limiting thing, because as soon as this guy is done, then we just jumped on and started reusing that memory, because what we just loaded up before has now been used and we don't need it anymore. Technically, EBX, ECX, and EDX, when we get to this line, still has the same 3 things in it. We just aren't using it anymore. We just overwrote EAX and said, you know what? I just want to exit the program now. Linux says, okay, no problem. We'll exit the program. I don't need any inputs, so I'm not even going to look in these places. Yeah, as soon as the next program gets onto the CPU, he unpacks his bags and picks up where he left off, and he has the registers filled up with the data he left off. All right, so quite a bit of crap happening behind the scenes. All right, And we really just touched the tip of the iceberg, right? We could imagine we start getting into the details of the operating system and stuff like that. There's a lot more stuff going on. But understanding this level of detail here allows us to really appreciate typing in this and just clicking run. Does that make sense? Imagine how much just occurred behind the scenes for all that to happen. A lot, right? Now, I mentioned earlier about this stuff up here. I'll just show you a quick example. It's for command line arguments, and we've actually seen it already by example today. When I run GCC, so let's pretend GCC is a program that we wrote, kind of like our Hello World program. Somebody wrote a program called GCC. Now, when they run this program, I'm passing it a single input. That's a string, that's my input. I'm going to go ahead and change this guy. I'll run this again. I'm just going to pass it some command line inputs. All right. So I compiled my thing, and all my program does right now is it's going to output the number of individual things that I passed it as inputs. Even though I'm not using those things right now, it's going to keep track of those number of things. So it says, you gave me 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, and then 9 is the name of the program. So those parameters there, this stuff, argc is the argument count. How many parameters did you pass in? argv is the values that live at those locations. I'll show you that by example real quick. Yeah. So I said 3. So this is 1, 2, 3. So it should be ASD. There's the ASD. That's the third thing that I passed in as a command line argument was ASD, in case that was going to be meaningful to my program. You know, if I had my program print out, you know, if I said cat, dog, elephant, and I wanted it to print out the second animal that I put there at the command line, it would be able to do that and use command line arguments if that made sense in our program. Most of our modern programs are not going to use command line arguments anymore, because a lot of times they're handled through graphical user interfaces and stuff like that. All right, homework for Tuesday is to get your set up an account on online GDB and get a Hello World program working, and click run and give me a screenshot of your working environment. All right, so all of you will have a Hello World program working by Tuesday. Sound good? Questions, comments, concerns, bribes? Go ahead. I'll put it on Blackboard. So there'll be a Dropbox on Blackboard later today for you to upload your screenshot to. All right, I'll see everybody on Tuesday.